Okay, so first of all, can everybody hear me? Is it okay now? Okay. So as Sarah said, almost all of my PhD research has been on this problem of figuring out how to search for gravitational waves using pulsar timing arrays, coming up with new algorithms, trying to speed these things up. And a lot of this has been work with my advisor, Javi Siemens, and some of the recent work I've been doing has been with Sarah. So just as an overview of the talk, first I'm going to go through some of the basics of pulsar timing experiments, a very quick overview of how pulsar timing works, and then I'm going to go over some of the actual sources of gravitational waves that we're looking for that are in the pulsar timing band and how they relate to the frequencies of LIGO and LISA, or a LISA-like mission. And then I'm going to deal with two kinds of sources. I'm going to look at some searches and predictions of what we'd expect from a stochastic background of gravitational waves. And then I'm going to go through some stuff about how you would detect and do parameter estimation for single sources of gravitational waves that stand out above this background. And then finally, in the end, I'm going to show some upper limits that we've recently gotten on the strength of these continuous gravitational waves. Okay, so first, very basics. So pulsars are highly magnetized, rotating neutrons. Here's the canonical picture that everyone uses in every talk. But for the kind of experiments we're doing, we don't want just normal pulsars. So there's a big category of pulsars up here in this PP dot diagram. So this is the period derivative of the pulsar, and this is the period. And so up here we have sort of the canonical pulsars that have order of a second spin period, and around, their spin down is around 10 to the minus 15 seconds per second. However, most of these have really, really nasty noise properties and pretty broad pulses, and you can't time them very well at all. So what we are interested in are these millisecond pulsars down here, which, if you haven't guessed by the name, they have millisecond periods, and they're much more stable. They have much smaller spin down rates. So they're very, very stable clocks. They're almost, they can rival atomic clocks in how well you can time these. And so as a very cartoon-like picture, which I'll play for a second because you might have a seizure. So you see this radio jet come into your line of sight, and when it goes through your line of sight, you can see basically a peak in the power that you're measuring. And in a very cartoony way, what we're doing is we pick some fiducial point on this peak of the radio jet, and you call that your time of arrival. In principle, it's way more complicated than that, but sort of as a cartoony way, that's the way you can think of it. It's when this radio pulse got here to the best that we can measure. So a very important thing about pulsar timing is what kind of model you use to do the timing. And so what we want is we want something that takes into account everything that we can think of that happened from when the pulse left the pulsar to when the pulse gets to the Earth. So this takes into account things even like the planets, the motion of the sun, the fact that the pulsar has some period and that it's spinning down. And so a very basic model for the phase of the pulsar is just some initial phase, which is just going to be some constant offset that we're going to fit. Basically this Taylor series type thing. So you have the spin, the frequency times time times frequency derivative times time squared. So I might say this without noticing it today. Sometimes I'll talk about quadratic spin down. This is what we're talking about. This is the main thing that affects your timing model because you're fitting out a quadratic out of this time series. And then you have other things. So you have to take into account the fact that we're on Earth, the telescope's on the Earth, it's going around the sun. So you have to take that into account. You have to have the sky location right, or else you're going to get these big year sinusoids in your data. And then most of these pulsars are in binary systems. And so you have to take into account the fact that the binary has some period, and you might be able to measure some post-Newtonian effects, which also come into this timing model. And so the data that we're looking at, I'm going to talk about this all throughout the talk. I'm going to keep saying residuals. So the residuals are just the measured time of arrival that you get from measuring the actual power from the radio telescope minus this model. And the way that you do this is it's sort of an iterative procedure. It's really some of an art to get close to the global maximum of these parameters. And then once you do that, you can do linearly square fitting, And this is done by a very common package in the pulsar timing community. It's called TEMPO or TEMPO2. And what that does is it spits out these residuals after doing a least squares fit. And so just to give an example, so what some real pulsar timing data looks like, this is one of our best pulsars from the NanoGrav array. So NanoGrav, it's a North American nanohertz observatory for gravitational waves. It's quite a mouthful, but it's basically the North American group that's dedicated to finding gravitational waves using these pulsar timing arrays. And so I don't know if you can read this axis, but this is the residual in microseconds. And so you can see here the spread is much less than, it's on the order of a microsecond. But also, as you can see, the uncertainties on these residuals are not even close to uniform. They're very different across the band. And this happens for multiple reasons. One of the things is you're observing these at different radio frequencies, so the pulsar might be stronger at different radio frequencies. Certain days, the SNR of the pulse that you measure is bigger, so you can measure the time of arrival more accurately. So we have a big spread in the error bars here. But if you take the weighted root mean squared of this, you get something on the order of 100 nanoseconds. So on average, we can measure the time of arrival of these pulses to within 100 nanoseconds. As an example of what happens if you get one of these timing model parameters wrong, so if you have your spin down wrong, you're going to see something that looks like a quadratic. That's how it comes into the model. If you get your sky location wrong, you see something that has a sinusoid at a period of a year. And this comes into play later because this can look exactly like a continuous gravitational wave. So you really have to take into account the timing model and the gravitational wave search simultaneously, so you don't end up either mistaking an error in your timing model for a gravitational wave, or just absorbing all the gravitational waves into these timing model parameters. So another cartoony picture of how this works. So in the absence of any gravitational waves, you just see these radio pulses coming from the pulsar to Earth. They're a nice steady train of pulses separated by the pulsar period with this very, very small spin down. So these are very regular pulses that you would see. However, if there's a gravitational wave passing by, then it stretches and expands the space in between the Earth and the pulsar. So it's going to induce a redshift here. So some of the pulses are going to arrive earlier, and then some of them are going to arrive later. And just the order of precision that we can get on measuring these pulses, or at least measuring the spin of the pulsar, as an example, for this pulsar, which again is one of our best timing pulsars, on this date, this is the period that we can measure with this uncertainty. So I think there are 14 zeros behind the decimal place there. So that's incredible accuracy, which we can measure this, or incredible precision. And so to give an idea of the kind of precision that we actually need to measure these gravitational waves, from most models that we know, the gravitational waves are going to give us perturbations in these residuals on the order of tens of nanoseconds. And so as I showed before, we can already measure these residuals on order of 100 nanoseconds. So we're getting really close to this sort of, this level of precision. And if you have multiple pulsars, you don't quite need, you don't need 10 nanoseconds precision in all of them because you're looking for a correlated signal in all of the pulsars. And so that brings us to pulsar timing arrays. As I mentioned before, we have NanoGrav, which is the North American group. There's the EPTA, the European Pulsar Timing Array. So the North American group uses the Green Bank Telescope in West Virginia and the Arecibo Telescope in Puerto Rico. The EPTA uses a slew of telescopes all throughout Europe here. And finally, the Parkes Pulsar Timing Array in Australia uses the Parkes Radio Telescope close to Sydney. And so it's good to have complete sky coverage here. For example, there are some pulsars, actually one of the best pulsars you can only see with Parkes. So the goal, what we started forming over the last couple years, is this International Pulsar Timing Array. So the goal is we're going to take data from all of these pulsars and combine them to have the best possible, longest baseline data set that we can get. And at the moment, we have more than 30 pulsars timed at or below the nanosecond, or at or below the microsecond level. And so the goal is to keep timing these and to add more pulsars. Especially adding more pulsars, which I'll show later, is one of the best things you can do to raise your chances of detecting gravitational waves. So now I want to move on to some sources of gravitational waves that we'd expect to see in the pulsar timing band. So throughout this talk, most of the sources I'm going to mention are from supermassive black hole binaries. So these are the black holes in the center of galaxies that have collided. And there is evidence for galaxies colliding, as you can see here. And there are a few candidate sources that would actually be at orbital separations close enough to be emitting gravitational waves. But one of the things that most people are focused on is the stochastic background. So this is sort of a superposition of lots of these supermassive black hole binaries at large redshifts. So what these do is they basically give you a bath of radiation that looks like some sort of correlated noise source. And it's hard to see in here, but one of the assumptions that we make is that there are so many of these sources and they're distributed isotropically on the sky. So you have a nice isotropic background of radiation. However, recently, some work has shown that, in fact, it's probably not quite isotropic. You probably have more of an anisotropic background where you have a few of these single sources sticking out, or maybe just some a group of sources that sort of form a hotspot in the sky, getting rid of the isotropic nature. However, for this talk, most of the stuff I'm going to focus on is on the isotropic background, mainly because this field really just got started, heavy duty into this probably about 5 to 7 years ago. So it's still a pretty new field. We're still developing techniques, so we're starting off with the easiest thing first, and most of the models that we use are for these isotropic backgrounds. And so the way that we usually define the background is in this strain spectrum, so we usually just have an amplitude and a spectral index. And so throughout the talk, I'm going to mention amplitudes like 10 to the minus 15, 10 to the minus 16. These are all amplitudes measured at a frequency of 1 over 1 year. So it's a kind of stupid unit because you have to basically project the amplitude back to that frequency. But this is sort of the standard in the field. And so to give you an idea of what kind of frequencies we're probing, pulsar timing arrays are down here around the 10 to the minus 9 to 10 to the minus 7 hertz. So we're down here at pretty low frequencies, whereas LISA is more around here the millihertz regime, and then we have LIGO up here in the kilohertz regime. And again, on here, there are 2 predictions. These are the best predictions for the level of this stochastic background. So the red here is cosmic strings, which I'm not going to talk about at all. The main thing we're focusing on are these supermassive black hole binaries. So these limits here correspond to some recently published limits, which I'm going to get into later. And you have this turnover here because at higher frequencies, there aren't enough of these sources emitting at these high frequencies to really contribute as much to the background. So if you might expect to see, well, you would expect to see more sources standing above the background down here. And these curves, this top blue curve, 2010, this corresponds to at least the best published nanograv limit, which is 7 times 10 to the minus 15 at a frequency of 1 over 1 year. And so right here, we're just starting to graze this sort of the upper limit on the expected distribution of these sources. But as I'm going to mention later, we've done some simulations, some projections up to 2015 to 2020. And these simulations show that around 2015 to 2020, we should be right into the meat of this distribution or being able to probe all the way through this distribution. So at this point, either we will have made a detection of this background or we'll be able to rule out all of the models that contribute to this gray shaded area here. I would much rather have a detection, but either one would still be interesting. Okay, so I've talked about stochastic background, which are lots of the single sources. Another thing is the single source themselves. What does this look like? So anyone in LIGO is used to seeing a waveform like this. Basically, the waveform that we see is this standard chirp waveform. However, instead of probing things way down here close to the merger, we're seeing stuff much farther out here, where this is, again, meant as a cartoon. I mean, we're actually much farther from the merger, but what we're seeing is basically a monochromatic signal at the Earth. So this is the gravitational wave perturbation at the Earth. And we see another monochromatic signal from the gravitational wave perturbation at the pulsar. But this is at a lower frequency than the Earth term. And so when these two things combine together, your induced residuals look something like this. So you sort of get this high frequency feature from the Earth term and a low frequency envelope from the pulsar term. And in fact, by having this pulsar term, you can do lots of cool things that you couldn't do otherwise. Because if you only had the Earth term, you're only going to have monochromatic signals. You can't measure any frequency evolution or really anything evolving over more than a 10-year time scale. But the pulsar term, because these pulsars are kiloparsecs away, you're basically seeing about a few thousand years in the past. So you can measure orbital dynamics over thousands of years as opposed to your observation time of 5 to 10 years. And so basically what this does is it gives you sort of a time machine to go back and probe these supermassive black hole binaries. And just one other thing I wanted to mention, which is one of the major differences between pulsar timing arrays and LISA-like or LIGO experiments, is that we're pretty much guaranteed to be in the low signal to noise regime, at least in the beginning. We can only see a few tens of cycles within our observation time. And so it's not like we're just going to go out one day and we're going to see this gravitational wave happen and then it's going to go out of the band. It's in the band right now. So right now the gravitational waves, if they're there, they're in the data set right now, just sitting below the noise. So what's going to happen, the signal's not just going to pop out of the noise is going to gradually get smaller until we can start to see the signal. So because of this, we're always going to be in the low SNR regime, at least in the beginning. And also because of that, all of our analysis is sort of tailored to the fact that we will have a low SNR. Okay, so this is sort of the current picture of what we'd expect in terms of gravitational waves and a little bit in terms of single sources. So this is from a paper, I said 2012, I actually think it was published this year, it was in the archive in 2012, by Alberto Susana. And so what he did here is he took, so he used the galaxy merger rate from actual observations to populate the gravitational waves. So he had the galaxy merger rate from observations, and he had basically the galaxy to black hole host relation, or you could figure out the mass of the black holes given the mass of the galaxies through a bunch of different models. He did a huge sort of systematic simulation using all of these different models so you can get a distribution of the amplitude that you would expect from these supermassive black hole binaries. And these curves are just using different models. So the most optimistic one here shows that there's a mean at about 10 to the minus 15, and again, this is reference to a frequency of 1 over a year, with 1 sigma uncertainties around 5.6 times 10 to the minus 16 at the lower level, and 2 times 10 to the minus 15 at the upper 1 sigma level. And this blue area shows the region of parameter space basically that we've been able to rule out by observations. So the Parkes pulsar timing array has an upper limit very close to 2 times 10 to the minus 15. So basically can rule out anything higher than that from that recent analysis. And so just to give a flavor of how these things, how you can get single sources from this, and on average, you would expect some curve that looks like, this line right here. But for the one universe we have, the one realization we have, you really get something much spikier like this here. So you have all these single sources down here contributing to this overall background. But it is possible to get strong sources standing out above the background that can be individually resolvable. And this just assumes that the evolution is completely driven by gravitational wave radiation. And this assumes that there is some gas in your system and there's some standard accretion rate, and many assumptions go into this that are sort of unknown. But what this shows is that if you do have gas in your system, which you probably would because it's colliding galaxies, not just black holes themselves, what this does is this drops off some of the power, flattens out some of the power at low frequencies. So these systems merge faster. They're not spending as much time at these low frequencies. And because of that, you might see a few more of these sources standing out above the background that can be individually resolved. And so that gives us a little bit of hope that, if this is the case and we can't see the stochastic background, we still might be able to see these single sources. Okay, so I'm going to sort of briefly go over what you have to do to search for these backgrounds, and then I'm going to go over some recent predictions that we've done that lead to those updated sensitivity curves that I showed a second ago. So as I mentioned, one thing that makes this different from LIGO and LISA data analysis is that we have this timing model that we've had to subtract out of the data. And you can look at this in terms of the likelihood function. So this is just a standard multidimensional Gaussian likelihood function. Delta t are the residuals. M is basically the design matrix. So these are the basis functions for the timing model. And these delta c's here are basically the parameter offsets. So if you're used to something like a Fisher matrix, this is similar to that. So we're assuming that the model parameters that we get from doing the pulsar timing, the linear least squares fitting, are close to the true values that we can describe it just by some linear offset from the true values. So this is sort of like doing a Fisher matrix type analysis for the timing model parameters. So if you have this, in principle, you could search your gravitational wave parameters, parameterized here by theta, and search these timing model offsets at the same time. However, if you have 40 or so pulsars and you have 20 or so timing model parameters for every pulsar, plus the gravitational wave parameters, plus noise that comes into your covariance matrix, you end up with a very, very large parameter space that you would have to search somehow through MCMC or test or something like that. And that gets to be a pretty difficult problem. So what you can do is you can analytically marginalize over these timing model parameter offsets. So this way, you're still taking everything into account. You're taking into account the correlations between the timing model parameters themselves, correlations between the timing model parameters and the gravitational wave parameters. But now you've greatly reduced your parameter space by analytically marginalizing over all these timing model parameters. And so this here is just sort of a schematic to show you. And actually this was, or at least this notation here, which is much more computationally efficient than previous ways of doing this, was actually developed by Rutger van Hasteren, sitting right here. So the way that you can think about this is you can think about it as just another standard Gaussian likelihood, but now you have sort of a covariance matrix and a new data set that are sort of projected onto some subspace that's orthogonal to the timing model. So it's basically now you just have a new covariance matrix that has the timing model sort of subtracted out and a new set of data that is reduced in dimension because you've subtracted out degrees of freedom from this timing model fit. And so this is the basis of everything that we do. And if you don't do something like this, then very bad things can happen where you can absorb all of your gravitational waves into certain timing model parameters and you would never detect anything. So doing this, we've shown through simulations, can save you from things like that happening. So the idea of the stochastic background search, and just as an aside, we do everything in the time domain for multiple reasons. One, because we subtracted out this timing model, which basically makes the data non-stationary, so it's very tricky to be able to do things in the Fourier domain. And like as I showed in the beginning, we have extremely irregularly sampled data. So we'll have lots of points separated by a few seconds, and then we won't have any points for a month. We might have a gap of a year. It's extremely irregularly sampled, so staying in the time domain is the safest thing that we can do. And so sort of a reduced version of this likelihood function I showed a second ago, where now these R's are what I showed before. So everything here is after you've done this marginalization over the timing model. But now this is for the full pulsar timing array. And so what you want to do is you have this covariance matrix, and the thing you're looking for is the correlations. The correlations between pulsars is how you're going to measure this background. And the correlations are parameterized by, at least in the pulsar timing community, famous Hellings and Downs curve. So this tells you how correlated two pulsars are as a function of angular separation in the sky. Right, so if you have a pulsar here and a pulsar here, and a gravitational wave is coming by, then it's going to stretch in this direction and compress in this direction. So these pulses are going to get here later, and these are going to get here earlier. And so if you change the angular separation, that correlation changes, and it's described by this curve. So basically, all of the information about the correlations are encoded in these off-diagonal autocovariance or cross-covariance matrices. But the problem with this is, all of these are block matrices, which are the size of the actual data set themselves. And you have to take this matrix and invert it for every iterations. So if you do something like an MCMC or some sort of nested sampling, you probably need about 1 million or so iterations of this likelihood. So you're going to have to invert these huge, some on the order of 50,000 by 50,000 matrices every iteration. And this is going to take forever, and it's not very feasible at all. So one of the main areas of research is how you can still do this completely correctly, but speed this up. And so there have been lots of effort going into this, and we've basically gotten this down so that we can speed this up orders of magnitude, so now it's possible to run within up to minutes to a few days for different kinds of methods. So I just wanted to give you a flavor of how this works here. I was going to go through much more detail talking about all of this, but I think it would be pretty boring. So more exciting, at least more exciting to me, is figuring out how our sensitivity to these gravitational waves scale as a function of some simple time or pulsar timing parameters. So what we've done here is we've used the optimal statistic, which is sort of a proxy to this Bayesian analysis. It's basically measuring the power in the cross correlations, which is the thing that you really want to know. And so you can sort of ignore these equations. But what we're doing is we want to see how the signal to noise of the cross correlations scales with time. And so what we've done is we've analytically solved this using this optimal statistic. And you see that there are sort of two different regimes. Here you have one scaling with time, here you have another scaling. And so in the weak signal limit, which really prior to us doing this work, when most people did projections for the future and sort of estimated what you would need to make a detection, they used a scaling like this. So at that point they were saying, well, more pulsars is good, but really if you just wait, since the scale is like t to the 4.33, at least in the case when you're looking for a background from supermassive black hole binaries, if you just wait long enough, eventually you get to a really high SNR and you'll be able to detect this. But that's really not what happens, because what happens is you have, like I said, you have information at the Earth, but you also have information from the pulsar term. And so the signal at the Earth is correlated, and the signal at the pulsar term is uncorrelated. So you have this signal growing and growing in the Earth term, but you also have the signal growing and growing in the pulsar term. And since what you want is the correlated piece, and not the uncorrelated piece, basically this pulsar term is just adding noise. So even if your signal gets bigger, you're adding just as much noise. And so then you start to hit this intermediate regime. This is basically when your signal is about equal to the intrinsic noise in the pulsar. So this is really the regime that you would make a detection in. And you can see this scales a lot different. M is the number of pulsars, so it still scales linearly with the number of pulsars. A is the gravitational wave amplitude. Sigma is basically the RMS uncertainty in your residuals, and T is the observation time. So now instead of scaling like T to the 4, it scales like T to the 1/2. And even more important is now instead of having this 1 over sigma squared, so this says that you need lots of good pulsars because your sensitivity goes like 1 over sigma squared, now it goes like 1 over sigma to the 1/4. So this means that you don't need pulsars that time nearly as good to be able to detect this background. Really what you need is just lots of pulsars that are timed reasonably well. And so to get an idea of how well you need to time these, if you have a 10-year data set, or really any of these, so I'll just pick 10 years. If you have a 10-year data set, if you want to be able to have your pulsar so that the signal to noise will scale with this regime, then even if you have the lowest estimate of the background, you only need about 700 nanoseconds. Which previous to this, people said, well, you need like 20 pulsars at 50 nanoseconds to be able to detect the background. We have lots of pulsars around this level. We only have a few around 50. So this is good news for us in that we wait a little bit longer and we keep adding more pulsars, even if they're not as good as we thought they needed to be, then you still can make a detection. And in fact, if you just added 10 pulsars with a really low RMS, you would actually have to wait longer for a detection than you would if you had lots of pulsars with a not quite as good of a noise level. And so, like I said, these are all just scaling laws, analytic relationships, but we took this and we ran simulations using the optimal statistic, not the scaling laws, actually doing the real thing. And so in these simulations, what we took was we took the current data set, so the current pulsars we have, the current noise levels we have, or scheduled up in 2014. So we're timing I think, 30-some pulsars now, and by 2014, we're supposed to be timing 42 pulsars. So we know which pulsars they are. We know the relative noise level, so we use those up to 2014. And then after that, we add 4 pulsars per year, which is about the average of what we've been doing over the last couple years, 2 with the Green Bank telescope and 2 with Arecibo. And they both have the median noise of the current pulsars that we have. And this median noise is around 300 or so nanoseconds for each pulsar. And so if you do this, and you add these pulsars with time, and you have some injections of different backgrounds, or different amplitude backgrounds, so here the red is this upper limit that we expected, and the blue is the lower limit. Then what you see here is this is the detection probability as a function of time. So this is the actual year that we would be in right now. So 2010 is where our current 5-year data set limits come from. And so you can see in 2010, we're way down here. We wouldn't expect to make a detection. But if we take this 2010 simulated data set and you use that data set to then compute an upper limit. So you say, well, this is the data set we have. What's the upper limit on gravitational wave background we can set using this? And if you do that, you get almost the exact upper limit that we have for our real data sets. So that really gives some credence to these simulations that they really do have the real sensitivity that we have in our one real data set that we have. And so looking at this, this tells you that the earliest detection, or at least at 90% detection probability, could come as early as 2017. And sort of in the worst case, if we happen to have a much smaller background than we would expect, at least within this model, we might have to wait until around 2025. However, this only includes the nanograph data. This doesn't have all of the data from the European or the Australian pulsar timing array, which goes back much further in time. So I imagine we haven't done this simulation with the other pulsar arrays, but if you take this for the IPTA, it's probably going to push these back, at least the least sensitive ones, push them back a few years. So I would say a detection, if these models can be trusted for the level of the background, is pretty much imminent within at least the next 10 years. Which might not sound that great, but the earliest detection we're predicting is around 2017, which I think is in line with what LIGO would predict for the first detection. Oh yeah, and just to show that these scaling laws do hold, so as I said, this is adding pulsars with about 300 nanoseconds every year, 4 pulsars, 300 nanoseconds. We have another simulation here that we've added 4 pulsars with 100 nanoseconds. So if you had the original scaling, you would expect the difference between these SNRs to be about 9, 1 over 3 squared. But if you look at these, there's almost no difference. This is just shifted by about a year in terms of detection probability at 90%. So this really shows that, even for real data that have differing time spans, different noise levels, things like that, you still get this scaling that shows that the noise level, as long as it's not really big, is not that important. Okay, so now I want to go over a little bit about what you do with single sources. So single sources, you sort of have some new parameters that come into play. Since for the background, we were assuming that it's isotropic and it's uniform across the sky, we didn't care too much about basically our antenna pattern functions, like how sensitive we are to gravitational waves at different points in the sky. But a single source is very dependent on that. So you can write a single source as basically a sum of these antenna pattern functions. So this is sort of the sensitivity to gravitational waves with a plus polarization. This is sensitivity to gravitational waves cross polarization times this delta S here. So what the delta S is it's just this difference of the gravitational wave perturbation at the pulsar to the gravitational wave perturbation at the Earth. So this is what I was talking about before. This is how you can get this sort of envelope pattern from having both the pulsar term and the Earth term in there. And so just to give you an idea of how these scale, we're using the 0 PN order, which is completely reasonable given that these things are at frequencies of a year. The higher post-Newtonian orders don't really come into play at all, at least for circular orbits. So the way these things scale, you basically get that the induced residuals scale like mass to the 5/3 over the distance of the source times frequency to the 1/3. So basically we want really massive things as close as possible with low frequencies. And basically the things you have to worry about are how the phase evolves. So for the Earth term, since there's no frequency evolution, this is really easy, initial phase plus omega naught t. For the pulsar term, which I've added flames here, because this is actually a very tricky data analysis problem, is that now this phase depends on the pulsar distance and the frequency of the pulsar depends on the pulsar distance. But pulsar distances are only known to within, at best, a few percent, most of the time 20 to 50%. So you don't know these pulsar distances nearly well enough to just fix them in your analysis. So it's like doing your LIGO experiment, but having no idea how long the arms actually are. So we have to add the pulsar distance as an extra search parameter in all of our analyses. And being able to keep this phase constant, or at least nearly constant, while changing the pulsar distance is quite a tricky computational task. So that's why that was in flames, because it's pretty hard to do. And a very reasonable assumption that comes into these, which is true in almost every regime we could expect for these sources, is that they're slowly evolving. So basically, there's no frequency evolution over, say, up to a 20-year observation time scale. But you do get this frequency evolution over the thousands of years between the Earth and the pulsar. So that's how you can sort of measure the dynamics 1,000 years in the past. And so here's an example of what I was talking about, that now we have to take into account how sensitive we are to different areas on the sky based on what pulsars we have. So with these plot, what the z-axis is here is basically a normalized SNR. So it's normalized to 1, and this is purely just analytic based on where the pulsars are and what the antenna pattern functions look like. But you can see if we have this full international pulsar timing array, which has this extra pulsar down here, 0437, so this is the one I was talking about. It's one of the best time pulsars, but you can only see it with parks. Then you get reasonable sky coverage. Most of our pulsars are here, and you're most sensitive closer to the pulsars. So you get really good sky coverage over in this area of the sky. 0437 basically picks up all the slack down here, but you're still left with a fairly blind spot up here. On the other hand, for nanograv, we don't have 0437 because our telescopes can't see it. It's too low in declination. Almost this whole area of the sky is blind to us. This presents us with a new problem in that you would need much louder sources coming from that area of the sky to be able to see them. And unfortunately, most of the these are sort of candidate supermassive black hole binary systems. So we expect that there could be these kind of sources emitting at the frequencies that we could see in systems located here. So most of the stuff is in this sort of blind region, which again advocates for having more pulsars. If we could find another 0437 up here, we would pretty much have the entire sky covered. Okay, so now a little bit more technical, but not too much. So the way that we do this, like I said, you have a fairly large parameter space. You have your noise parameters. So the easiest way you could do this is to model each pulsar as having 4 different noise parameters. Then there are 8 gravitational wave parameters, but now you also have the pulsar distance as another parameter. So if you have 10 pulsars, you have 10 pulsar distance, 8 gravitational wave parameters, and 4 times 10 noise parameters. I can't do math in my head well enough, but that's a fairly large number of parameters. And so what we do to get around this problem is we use a Markov chain Monte Carlo algorithm, which anybody in here that does LIGO stuff is probably very familiar with this. And so most of the work that I've been doing with some collaboration with a few others is to develop an MCMC code that can explore this parameter space efficiently. And we use some adaptive MCMC techniques. So this will tell you, how far you can move in parameter space and still be efficient. We use differential evolution, which is the easiest genetic type algorithm that you can do that will allow you to use the past history of your samples to figure out better places to move in parameter space. And we use parallel tempering, mainly just to get onto the global maxima in parameter space as quickly as possible. And so this is a cartoon of how our pipeline works. So the first part you have is the search phase. So you're searching around parameter space. In this case, it's only one parameter, but in reality, you're going to have about 100 or so parameters. But you're searching around parameter space, and then eventually you lock on to this global maxima, which is what the green line is here. Once you've locked onto that, you want to collect a lot of samples to get the probability distribution of these parameters. And once you get these samples, you can then use all of the different temperature chains that you use from parallel tempering to evaluate the evidence. So the Bayesian evidence is usually how we compare models. So you would run this kind of search for a gravitational wave plus noise model. You would do all of this, you would get a value of the evidence. That tells you basically how well this model matches your data. And then you can do this run again just with the noise parameters and get the evidence for that. And then take the ratio of the two, and that is what we call the Bayes factor. So again, anyone that does LIGO already knows this. But this is basically our detection criteria. So we're going to do this search and evaluate the evidence, and then look at the Bayes factor and see whether or not there's really evidence for a gravitational wave, or if there's more evidence that it's just noise. And so this sort of pipeline is in place, but it's still in development. Again, very similar to something like Lau inference in LIGO. It's currently in development. We're trying to make it as efficient and fast as possible. So just some sort of caveats to this, some bad things that can happen. One is that you're very, very dependent on your noise realization. So here we've done some simulations with the exact same gravitational wave injection with the same random number seed. So these noises, for each of these curves, the random number seed, so the noise is exactly the same, it just has a different signal. And so you can see for some realizations, you can make a detection. So a detection would be somewhere around a log Bayes factor of 5. You can make a detection with an injected SNR, say, of 5. However, for some other unfortunate realizations, you might have an SNR even of 8, that you still don't have enough evidence to make a detection. And it's something that we're really starting to realize now, which is sort of more important than this, is you really, really need to have a good noise model. So this is a run using real data that we didn't use the right noise model. We didn't model some low frequency noise, so what happened is the gravitational wave basically picked up on that low frequency noise and modeled it as a really low frequency gravitational wave. And so if you look at this, it gives you a nice sky location. It's very localized in the sky. It has really tight frequency measurement. And the Bayes factor corresponding to this was somewhere around, well, I don't know if the log Bayes factor. The Bayes factor was somewhere around 50, which is not quite decisive evidence, but it's pretty strong evidence for a gravitational wave. But that was just because our noise model was horribly wrong. So the moral of this story is, if you use the wrong noise parameters, you're going to have a bad time. So modeling the noise, the detector characterization, is a ever-growing field in pulsar timing. So a lot of us are working on this now. And there are more and more things that are making us wary about these algorithms. So we're really, really trying to understand the noise. But it's not anything like LIGO because our detectors are in space. So you can't go look at the pulsar and see what's really going on. And so finally, using these methods, we can set upper limits on the strength of this background as a function of frequency. Or not the background. This is the strength of the individual source amplitude as a function of frequency. And so this analysis is all on the nanograph data. So it's a 5-year data set taken with the North American telescopes. But what you see here is you basically see this shape that looks pretty similar to a LIGO noise curve. So this upward turn here is because of the fact that we had to fit out this quadratic. So if you have a sinusoid that doesn't have a full wavelength, it looks a lot like a quadratic, and it will be subtracted out in the timing model. So you're losing sensitivity at low frequencies because of that. You have this big spike, much less sensitivity at a frequency of 1 year. So this is, like I said, this is from fitting for the sky location of the pulsar. So gravitational waves at a frequency of 1 year are much less sensitive because of this model fitting. And the two methods that we've used here, one I didn't mention, one is a frequencies technique, which is the F statistic, which again, anyone in LIGO probably knows what the F statistic is. It's a way that you can maximize over a lot of these parameters, so you don't have to search this entire parameter space. So you can do a frequencies technique with injections, and you get this red curve here for the upper limit. But if you do the Bayesian technique, then you get the blue curve, which is nearly identical. This is using the full parameter space and basically looking for the amplitude of the signal that would give you a 95, which is amplitude of the signal that 95% of the probability is below this value. So this is sort of the Bayesian upper limit way of doing things. This black curve is the expected upper limit we could get from combining all of these data sets. So this is just the one data set from Nanograph, but if you put the European data sets and the Parkes data sets with much longer baselines, then you expect to get something down here. So this is about a factor of 3 improvement in the upper limits from using these combined data sets. And corresponding to this plot, you can also think, instead of strain and frequency, you can think of mass versus distance. And so lots of people always ask me, well, what's your horizon distance? How far can you see a gravitational wave source? And the answer is not too good. So if you look at this, if you sort of pick a canonical gravitational wave or a supermassive black hole mass of 10 to the 8 solar masses, then basically the farthest you could see with these upper limits is somewhere around 10 megaparsecs. If you have a much more massive source, then you can get out to around, a little bit further out, maybe 50 or so megaparsecs. So we're still limited to sources that are pretty nearby and or massive. However, as I've shown here, just from adding this extra data, we already get a factor of 3 improvement. So if we keep timing these pulsars, we should be able to push this even further down this way. But something really interesting, so these are just a collection of different sensitivity curves like this for the different PTAs. If you take one of these simulations, like I showed before, so a simulation of all the single sources and how they contribute to the background, we're starting to get into the regime, at least with the simulations, that these single sources could possibly be very close to these upper limits. So based on the simulations, we're at least starting to probe the regime where you could expect to see single gravitational wave sources that stand out above this background. So this is extremely good news for us. It is possible that we could detect these things much sooner than we could think if we have a favorable realization of these sources in our universe. And finally, some of the newest work I've been doing with Sarah is if you do have an electromagnetic observation of one of these supermassive black hole binaries, how can you use that to try to boost your sensitivity in detecting them in the gravitational wave band? And usually the way this works is it's basically just Bayes' theorem, or if you think of it in terms of a trials factor. If you know something like the period or sky location, then you don't have to search as many trial periods or sky locations. So basically what we did in this simulation is really similar to those noise realizations we did before. We just injected signals at different amplitudes. And in one case, we used information from a fake E&M measurement of a gravitational wave, or of a supermassive black hole binary. And you can see that you can make a detection much earlier. So you can make a detection for an injected SNR around 4 in this case, whereas if you didn't know anything about the source, you'd need an SNR much higher. So this can really boost your detection. You might be able to make a detection sooner than you would otherwise if you have an E&M candidate that goes along with the gravitational wave candidate. And another way you can think about this is if you do make the detection and you want to know what parameters, what the mass, what the distance to the source is, you can use these same priors. So assuming you know what the period is and assuming you know what the sky location is, then you can get better estimates on something like the mass and the distance here. So here the blue are the probability distributions just from the gravitational wave. So assuming we know nothing about the source, and the green are the distributions when we do know something about the source. So here we can measure the mass and the distance marginally better. And so this is an ongoing area of research that we're trying to see, how much can you boost significance and how much better can you measure parameters. And since I'm about done, I'm going to leave you with some questions you might have about, are we making things too simple? So sort of the current areas of research moving beyond this isotropic background, circular sources, is what happens if you have an anisotropic background? What happens if you have multiple sources that stand out above the background instead of just one? What are the eccentricities? Are these sources really circular, or would we really expect something that has a much higher eccentricity, which will require much different search techniques? And this sort of gives you somewhat of a nightmare scenario of what could happen in these cases. So if you have really eccentric sources, then the amplitude of the gravitational waves will drop off, at some frequency, will drop off and even start to turn down instead of continuing up, as if you had circular binaries. So this is very scary if we do have something like this. So all of these things are an area of current research, trying to see if something like this really is the case. If it is, how can we improve algorithms to see if we could measure something like this? So as the field is evolving, we're getting, more and more realistic / nightmare scenarios to try to cover all of our bases. And I think that's it. What do you want? Oh. Yeah, so I think I did 5. So 2, 3, 4, 5. So around 5 times 10 to the minus 8, you get around 10. How many galaxies are there? Yeah. We're not actually sure what it is to 10 megaparsecs. Yeah. Well, the 10 megaparsecs is sort of the average value. So that's average over things like the inclination angle. If you happen to have a face-on source, then you could have a distance bigger than that. Basically, how much? I think almost a factor of, let's see, the inclination will change the strain. I think about a factor of 2. So 20 or so. So some of the hot spots, there's been some work on trying to find sort of gravitational wave hotspots. And I think the Virgo cluster is like 16 megaparsecs away. So that was the best candidate for where we would expect gravitational wave sources. But again, that's sort of biased by the fact that that's one of the closest ones. The Virgo and the Coma cluster, I think the Coma like 60 megaparsecs. So there are some galaxy clusters that are this nearby. There's this 3C66b gravitational wave possible supermassive black hole binary that I think again is tens of megaparsecs away. So like I said, this is fairly bleak, and like I said here, you're just approaching the area where there may be some detectable ones, and these detectable ones would be the closest sources. So really, you're going to have to probe a lot further down and get this horizon distance much further out to really have a good chance of detecting these. Yeah, so this scaling, unfortunately, is not as nice as the stochastic background scaling. So basically, this scales like the stochastic background in the weak signal regime. So you need more pulsars that are timed really well. So it has a 1 over sigma squared type scaling. No, basically well, it does have a factor like that, but that's just going to push this bucket down further. But once you do that, you're starting to hit into the stochastic background anyway, which is going to cover up any single sources. So you would expect something at higher frequencies. So yeah, the longer time span pushes that bucket down further. The more pulsars time better, it pushes the whole curve down. So that's why, really, I think for the best chance of detecting these sources, or more than one of these sources, is something like the square kilometer array. You're going to need something that can find lots of pulsars and time them really well. But it's still really interesting to look at these kind of things. And if you have something like eccentricity, then all of these things are completely different. So you might have a better chance of detecting an eccentric source than a circular source like we've looked at here. Yes. The scalings for this or the scalings for... So the stochastic background is not quite as sensitive, mainly because for these single sources, you're basically just seeing one frequency. So if you had some low frequency thing that can look like a sinusoid at low frequencies, that would completely wipe out your signal, or you could think it is a signal. So for the stochastic background, you can measure these sort of red noise, low frequency things much better. So it is still sensitive, and that's sort of one of the areas that we're starting to look at. So in all these analyses, we're assuming that you can measure the noise pretty much perfectly. I do know that I've done tests that basically show what kind of bias you would get on this optimal statistic from uncertainties in the noise. And if you just pick, you can do a noise search and you have some posterior for the parameters. You just draw parameters from that. So assuming that you've got some noise, right, that the true value is somewhere in that range. If you just do that, then you can get about 20% biases on the optimal statistic value. So I guess that would sort of correspond into, this SNR being 20% or so underestimated if you do a horrible job with the noise estimation. Oh yeah, so in that case, the scaling laws were derived under an assumption that is not quite true, is that there's only white noise. So we can measure the white noise. Yeah, we can measure the white noise very well. If you have additional red noise, which I didn't really mention in that slide, but I had basically 5 nanoseconds of red noise at 5 years. So currently we don't see any evidence for any low frequency noise. So it's sort of good news on that front, that we really only have to deal with the white noise, which we can measure reasonably well. We haven't included red noise, or red noise that isn't gravitational waves, in these scaling laws. So I'm not quite sure how that relationship would go. But if there is red noise, I did include red noise in the simulations, and you still get a similar scaling. Yep. Let me go back to that slide. Here? No, here. So, well, it's a caveat. All of my research has been on supermassive black hole binaries. I know that these limits come from whatever the best published limits are on the strength. So if you look at these kind of curves, then right, you're probing down into the background you could expect from cosmic strings, but you haven't gone all the way through it. And as you can see, this has a much bigger uncertainty. I'm not sure if these are 1 sigma uncertainties or 2 sigma. So the answer to that is I'm really not sure. All I can tell is gather what you can get from this plot. Yeah, so my advisor, Javi Siemens, he works a lot more on this cosmic string stuff. But really, in pulsar timing, there's been very, very little interest in cosmic strings. Most people are focused on these supermassive black hole binaries. Where is it? This one. It's still a prediction because I wasn't allowed to show the real IPTA data. So it really is pretty close to that. This is just sort of drawn on top of what the real curve would Yeah, so that's how I got around that. I just made a fake line on top of the real one. Yeah. To move through it, um, there's got to be at least hundreds of thousands, a million years or so, because the difference in the so over the pulsar Earth flight travel time, it's about a few thousand years. The difference in the frequency is only a few percent. It's not very big. So to completely move out of the band, which spans about 2 orders of magnitude, um, let's see. Well, it does depend on the mass. I'm not quite sure offhand, but it's a very long time, and we definitely wouldn't expect something to come into the band and go out of it in anyone's lifetime. Yeah, yeah, somewhere around there. Yeah, so these sources. Yeah, I mean that's basically how those distributions of the amplitude. That's basically how they got those, right? They took the known galaxy mergers and they have some relation between the galaxies and the host mass and the black hole mass, and they've just sort of iterated over those different models. So it's how likely is it that they have a merger given a certain mass? So yeah, so that's sort of what has been done already, and those estimates are fairly optimistic. Again, it's still assuming isotropic electricity, which if that is the case, which we don't know if it is, then it could be much worse. So I mean that the distribution of galaxies that you're using is isotropic in the sky, or at least the strength of the gravitational waves coming from them is isotropic. So if you had a clump of galaxies that had high masses, then that would be anisotropic because you'd have stronger gravitational waves coming from there than anywhere else. Yeah, I mean that is yeah, I think that is built in, but I guess you're not sure what the mass of the supermassive black hole is in those galaxies, and that's one of the things in the model that sort of averaged over in those simulations.